Hello everyone, welcome to our SAC ACM 2022 paper presentation, Representation Learning via Consistent Assignment of Views to Clusters. This is a joint work with Professor Dr. Adin Ramirez from the University of Oslo. Contrastive and non-contrastive methods for representation learning have significantly reduced the gap between supervised and unsupervised representations. These self-supervised methods work similarly. First, they simulate different views of a concept by applying a set of random transformations to the input image. Then, the goal is to learn a metric such that representations from these augmented images, or views, are placed closer to one another in the embedding space while they are positioned far apart from representations of different images. This idea is embedded in popular contrastive loss functions such as the InfoNCI, a popular loss function used in current self-supervised methods. If we take a look at the InfoNCI loss, however, we will notice that from a clustering perspective, the InfoNCI is enforcing a clustering objective at the image embedding level. In an ideal situation, we can interpret the training objective as learning n clusters, where n is the number of observations in the dataset, and each cluster is constrained to have only augmented versions of the same image. In our paper, we propose consistent assignment for representation learning, or CAR, an alternative method that combines deep clustering with recent self-supervised methods. Instead of modeling the problem as a clustering task at the image embedding level, we relax some of the constraints of the InfoNCI loss and learn a number of prototypes k such that k is significantly smaller than the number of observations n. In other words, instead of directly optimizing the views embeddings to look similar, as other contrastive methods do, we discretize the embedding space into a finite number of prototypes and enforce the views representations to be consistent among the set of learnable prototypes. Our training objective is designed to enforce different views of the same image to fall into the same prototype. However, since the number of clusters is smaller than the number of images in the dataset, now the clusters will aggregate representations from different images that share enough similarity to be associated to the same prototype. The steps are as follows. From an image, we create a pair of views by applying a stochastic augmentation function. We independently feed the two views to a Siamese ResNet encoder to obtain a pair of representation vectors for each view. Then, each representation vector is fed to an assigner that will produce a probability distribution relating a given view to the set of learnable prototypes. Finally, we learn the parameters of a Siamese encoder to produce similar probability distributions for both views. Our loss function includes two components. The first component is the consistency loss, which represents the negative log of the dot product between the views' probability distributions. This term enforces the distributions to be consistent and confident. That is, both views should be assigned to the same prototype with as much confidence as possible. Note that the negative log is minimized when the probability distribution for both views looks like equal one-hot distributions. If we only optimize the consistency loss, however, the network will inevitably find a shortcut and optimize the loss function by assigning all views to the same prototype. To avoid this undesirable trivial solution, we force a non-informative prior over the prototypes such that for an input batch of views, each prototype should have the same number of assignments. In other words, the average prediction within a batch of views should resemble a uniform probability distribution. In terms of results, we assessed the quality of the representations learned by Carl using the linear evaluation protocol on the CIFAR 10 and 100 datasets, on the STL10 dataset, and also using a smaller version of the ImageNet where the images were downsampled to 64 by 64 RGB observations. In this protocol, we take the pre-trained Carl self-supervised encoder and train a linear classifier on top of the frozen representations using the labeled data. As we can see, for all protocols, Carl achieves comparable results with concurrent work on self-supervised learning, such as BYOL and SimClear. We also evaluate Carl's pre-trained representations on downstream tasks such as domain transfer, semi-supervised learning, and when fine-tuning the entire pre-trained encoder. For most protocols, again, Carl performs equally well with the state-of-the-art representation learning methods currently available. For more information, please consider accessing our paper and our publicly available code. Thank you.